Hi, my name is Daniel Odamellam, and this is my ISP, the Custom Mechanical Keyboard. This project explores the data path of a modern computer peripheral and how it transforms physical tactile input into digital communication signals through a custom matrix, software debouncing, and USB HID protocol. The physical layout of this keyboard is 7x9 switch matrix, where 16 pins on the Arduino Pro Micro monitor 63 different switches. When a key is pressed on the keyboard, it completes a circuit within the matrix. To ensure the signal is clear, the current passes through a 1N4148 signal diode, which prevents ghosting, an occurrence when you press multiple keys and electricity backflows, and a key that wasn't pressed is registered by the host OS. When plugged in, the keyboard must first establish communication with the host OS. This happens through the USB handshake known as enumeration. The Arduino Pro Micro sends a human interface device, HID, report descriptor, to the host OS. This is a digital blueprint, which in this case tells the computer that I am a keyboard capable of N-key rollover. This identification process allows the computer to reserve specific loading docks, called endpoints, in its memory to receive the typing data. When a physical key press reaches the microcontroller, the firmware begins its work. A nested loop constantly scans the grid, but doesn't immediately take the signal it receives. Instead, because switches vibrate when pressed, the firmware implements software debouncing before sending an instruction. This process involves comparing the current scan of the matrix against a last state array, which is the stored memory of the previous scan, and then waits for a small settlement period. Only once the signal is confirmed to be stable does the firmware then convert it into a digital instruction to be sent. With the connection established and the signal received, the keyboard now needs to send the data. Instead of sending a string of key codes that represent individual characters, I use N-key rollover logic, NKRO, which means that I can press any amount of keys at once, and the host OS will accurately read this as opposed to 3 or 6 key rollover, where the computer will only read that many key presses at once, excluding modifiers like Shift, Alt, and Control from the count, before failing to register extra inputs. As such, the firmware translates the matrix coordinates into a 256-bit bit mask, which is a 32-byte array, where every key has a dedicated bit. Using bitwise OR operations to update the report, the firmware then flips bits on and off according to the signal received and sends this map to the OS every time it polls or asks the device for an update. The final important part of this keyboard is the function layer. As my layout doesn't include the F1 to F12 row, the firmware adds a second mapping layer through logic branching. By defining a custom function key at a value 0xFFFF, which is outside the possible HID instructions as the values cap at the 8-bit range and therefore it won't get sent to the OS, the key acts as an internal logic line. When the firmware detects this bit is active, it shifts the data path to the secondary function layer. This lets the keyboard act as a composite device, changing the inputs from the standard characters to the F1 through F12 functions and consumer control, allowing it to increase or decrease volume as well as play or pause music or video. This has been my custom mechanical keyboard ISP. My name is Daniel Odamellam, and thank you for listening.